Okay, so now we will solve this problem, and this is the isentropic efficiency of a steam turbine. So if we see the schematic here, here actually you can see this is a steam turbine, and we know this is the inlet, this is the outlet. So we know the pressure and the temperature for initial phase. Here you can see the pressure and the temperature for the final phase, the final state. And we can see some work output here, so we'll see. And here you can see the TS diagram, the temperature and the entropy diagram. So let's try to understand the problem at first, and then we'll try to solve this. So here what it says, the steam, it enters into this turbine and it is adiabatic. So it is adiabatic turbine, and the other one is keyword is steadily. So steam is entering into this turbine steadily, and it is an adiabatic turbine. And the temperature and the pressure is given. All informations are given, and it leaves through this exit, this outlet. The power input of the turbine is 2 megawatt. So this is actually the power output. So what we are getting this input. So this is the output through the exit, and this is the power output. So this one is output, this is output. We have this input. So now what we need to do is we need to determine the isentropic efficiency of the turbine. So we already discussed during the when I discussed the theories, then I said what is the isentropic efficiency of the turbine. We know the formula and the mass flow rate of the steam flowing through the turbine. So other important information given here, the isentropic enthalpy at exit of the turbine. So it is given, so it is 2407.9 kilojoule per kg. So this is given, and that makes our life easier, more easier. So that I will discuss gradually. So what we need to do, guys, at first we need to calculate the efficiency of this turbine, right? And then finally the mass flow rate. So isentropic efficiency, if you attended the lecture, you know isentropic means the entropy change, it will be 0. Try to understand this figure here, this TS diagram. So we will discuss second law, then we will see two different types of diagram, TS and the HS, temperature enthalpy, entropy, or enthalpy entropy. Anyways, so you see here, this is actually the, I believe you know the efficiency definition, isentropic efficiency definition. So if I want to discuss it, it will increase the length of the video anyways. So this is actually the actual processes. So this is state 1, this is a state 2, and this is actually the isentropic processes. You know, isentropic means the entropy change, it will be 0, so no entropy change. So this is the state 1, this is the state 2, as you can see. So when it is isentropic process, when we are telling isentropic processes, at this 2s state, the entropy is not changing, it's constant. So that's the main theme of this problem. Anyways, so now at first we will write down some assumptions. So the assumptions, if you see, guys, here, the first one we can say it is steady. So we can say that steady state operating conditions here. And the other thing is, we will see the kinetic, the change of the kinetic and the potential energy. So delta K E and the potential energy, delta PE, it is, the change is negligible, so we can say it is very close to 0. Right. So from the definition, if I know the first part of this problem, what we need to calculate is isentropic efficiency. So efficiency we usually define by eta, Greek symbol, and for turbine we say T. So eta T, we know it is equal, we know from the formula, this is H1, H2A, H1, H2S. So this is actually the formula. So here In this problem, it is given. So H2S, it is given. So the unknown variable is, you see this H1 and H2A. So what is H? It is actually the enthalpy, right? 1 means the enthalpy here. And 2A, that means it is here for the actual processes. So for state or the process 1, we know P1, T1. For the outlet, we know the P2, T2. So then we can use these values and we can actually calculate the properties. So here, what is the material? Material is steam. And if you look this TS diagram, so this is this dome-like shape. If you can remember from week 2, week 3, so inside this, it is actually the mixture region, right? The left-hand side, it is actually the compressed. And this is the right-hand side, just this section, this region is the superheated. So here it is the material is steam. So that means we need to use, here we will use the superheated table. So this is table S6, superheated water. What we will do, guys, we'll calculate the H1 by using these properties. We'll calculate H2A by using these properties. Okay, so let's do that. So what I can write for state 1, we know the pressure P1 is 3 MPa and T1 it is 400 degrees centigrade. So for this value, this two value, we will use table A6 for superheated water. So we know this is table A6, and what is the pressure? 3 MPa. Right. The temperature, it is 400. So for 400, if I draw a line like this, let's say, this is actually the enthalpy, 3231.7. Okay, if you need entropy, then this is the value, right? So we only need the enthalpy here. So now we will write for this one, H1, it will be 3231.7. This is kilojoule per kg. So we got H1. So now we need H2A. So now go to the state 2. For state 2, again the pressure, we will define this is a state 2. So we will say this is maybe 2A. We just put the name that way. So the pressure for this section P2A, it is 50 kPa. And the temperature T2A, it is 100 degrees centigrade. So if we use this two value again, so we need to use table A6. So table A6, but here now pressure is 50 kPa. So you can see this is 0.05 MPa, which means it is 50 kPa, and temperature is 100. So for this temperature 100, you will see, guys, this will be the enthalpy. So what we can write here, the H2A, it is equal, we got 2682.4 kilojoule per kg. So then you can see we have all the values like H1, we have H2A, and H2S, it is given. So all of these values given. So now what we need to do is we need to substitute these values in the expression, and we know that expression, the eta T, it is equal H1 minus H2A and H1 minus H2S. So look, in this case we actually we will, okay, let's substitute the value. So H1, it is equal 3231.7, H2A is 2682.4, H1 is 3231.7, and H2S, it is given in the question we know this is 2407.9. So we will get, the efficiency is 0.667, or you can say 66.7%. So this is actually the efficiency of the turbine. So we have done with the first part of this problem. I believe you understand. It was pretty straightforward. We just use these values and we subtract the enthalpy value for state 1 and state 2 from the table A6. And if you ask me why you use A6, because you can see this is the superheated region here. This point, the actual processes, it is happening at the superheated region. So now the second part of this problem is we need to calculate the mass flow rate, right? The mass flow rate. So here what is happening, guys? We are getting this pressure and this temperature through this exit. We have, you see, this 2 megawatt of the power output. So if we do the energy balance, and then we can easily calculate the mass flow rate, because in our assumption we said the kinetic energy and the potential energy change, it is negligible. So the only thing is we have the mass energy, okay, here, because it is coming to this way, it is going to this outlet. So what we can write, the section B, we will do some energy, okay, balance. Energy balance for a steady flow problem. Our assumption was steady. So for a steady flow problem, it is the energy in, it is energy equal to energy out, right? And the change is 0 because it is steady. So in, it will be equal to out. So for in, we have the mass energy here. So we can say it is M, the mass flow rate. And the only thing is we have, you can see we found the entropy, it is not changing, only the enthalpy. So right, so we can say, we know the formula actually, M Hayes plus enthalpy plus kinetic and the potential energy, but these two, all these terms are 0, so I don't need to write it. I believe you know actually already. So it will be M Hayes 1 equal, when it is the the energy out, we have this energy out, so we can say that work out plus M Hayes 2 through this outlet. Okay, I believe you understand this. So we can say that work output, it is equal M dot Hayes 1 minus Hayes 2. We just put this term to the left hand side, so it should be M Hayes 1 Hayes 2. You know this calculation, it is pretty straightforward. So this value is 2 megawatt. We will convert it into kilojoule per second. We know 1 megawatt, it is equal 1000 kilojoule per second. So we can write it this way. Mass flow, we need to calculate it into Hayes 1 3231.7 minus Hayes 2 is 2682.4. This is kilojoule per kg. So if we simplify this, then we will get the mass flow from here. So M, it will be 3.64 kg per second. So this is actually the mass flow rate. So here what we did, we simply used the energy balance for a steady flow system. And for a steady flow system, we have only this input, and this is the output, this is the output, energy output. So we did some simple calculation here. So I believe you understand. It is pretty straightforward, and I will tell you, just practice some similar problem for the next quiz in the final exam. So that's it.